Hello again. This is the last example, example 3 from class 18. And we're dealing with rigid body acceleration. And this is Coriolis acceleration. And I found one from Hibbler's 14th edition, problem 16-140. That's really long and complicated but does have Coriolis acceleration in there because it has the two ingredients most inquired. It has a angular velocity and it can slide. So here, this point, this part right here, its length can increase. So at the instance shown, rod AB has an angular velocity of 4 radians per second, an angular acceleration of 2 radians per second squared, and you can see that they're both counterclockwise. Determine the angular velocity and angular acceleration of rod CD at this instant. The collar at C is pinned and connected to CD. Yes. Okay. And slides freely. That's nice. So let me go all vectory onto this thing and say that omega AB is equal to 4K. That's what we're given, radians per second. That's a radians per second. And the alpha AB is going to be 2K radians per second squared. And if we take a look at this, because that's 60 degrees right here, we could say that the position vectors that we're going to want to get are, let's call it C with respect to A, is going to be 0.75 times the sine of 60 I plus a negative 0.75 times the cosine of 60. It's negative because we're saying that, and why are we saying that? Oh, that's C with respect to A. Okay, yeah, so we're using A as the reference. Yeah, that's why it's negative. Sure. J. And so if we had actual numbers here, 0.6495 I plus our negative 0.375 J. And for simply the RC with respect to D is going to be equal to a negative 0.5 I. And if we wanted to get aligned with the bar, assume positive. Okay, so the solution manual, it turns the coordinate axes to align with things, which would have been easier, definitely would be easier. Okay, but I think I kept it my way. Yep. So I say that I will want to eventually know V, how did I write this? I want to know VC with respect to A relatively, right? And that's going to be VC with respect to A times the sine of 60 times I, and then negative VC with respect to A. This assumes that they're positive, times the cosine of 60J, right? So we don't know the magnitude of it, but we do know the sense that it has to either go along, it has to go along that line. And we can have the acceleration do the same thing. Oh, and by the way, okay, well, I'll write it underneath there later. So this is the rel. That's supposed to be REL. So we go AC with respect to A, sine of 60, I, plus a negative AC with respect to A, cosine of 60. And I think some people actually memorize these types of things. This is 0.866, and obviously that is 2. And this is 0.5, and this is 0.5. Very familiar with this. All right, so we start out with a velocity analysis. Vel this. And we take the velocity of C is going to be equal to the velocity of A plus omega AB crossed with R, C with respect to A, plus V, C with respect to A, rel. Okay. And we say that's equal to 0, plus 4, we're given 0.6, whoops, we have to write this whole thing out. 0.6495 K crossed with I plus 4 times our negative 0.375 K crossed with J, all right, and then plus a 0.866 V C with respect to A I. That's what I'm doing is I'm using this guy right here, plus a negative 0.5 V C with respect to A in the J direction. All right, and if I were to work all of those out right there, including the fact that these guys right here, this turns into a J and this turns into a negative I, what we end up finding is we have 1.5 plus 0.866 times VC with respect to A I plus 2.598 minus 0.5 VC with respect to A and that whole thing J. Okay, you'll see what we're doing here in a second. It'll make sense. Now, okay, so this was for bar AC. Now for bar CD, we end up, let's use another color because we're getting bored, right? I'm boring the shit out of myself, the poopy out of myself. I shouldn't talk dirty. Don't talk poopy talk. All right, so we say the velocity of D plus omega CD crossed with RC with respect to A right here, and plus VC with respect to A rel. But that's 0 and that is 0. So all we're left with is the VC is going to be equal to omega CD times 0.5, negative 0.5, because that's this position vector up here. Look at that little guy stuck in right there. Boom. And where'd you go? Oh yeah, here you go. K crossed with I, because it's up here, I. And we know that's going to be a J. Woohoo, down here at the bottom. So what we're left with here is that VC is also equal to a negative 0.5 omega, not DD, not DD, CD. CD, it's a CD thing, and that's J. Maybe you can see what's going to happen here is that we're going to equate these two things, and we're going to be able to find the things that we don't know. Yay! Okay, so we have to remember what we wrote over there. But to go to the next slide. Here's the point part. We can equate the i's to each other, and that means that this guy has to be equal to 0, right? And if that's true, then we're able to figure out what VC with respect to A is going to be. And then we could plug it back into this guy right here, which is equated to the J, and we could figure out that omega CD. So you see the scheme that we had to do? It made it a lot easier that this bar is horizontal, because that makes one of the things 0. Otherwise, you have to do a simultaneous solution of these things, and who the hell wants to do that? So we know that 1.5 plus 0.866 VC with respect to A had to be equal to 0. Therefore, we find that VC with respect to A was equal to a negative 1.732, right? And that's going to be meters per second, according to this thing. And so that means that it is actually traveling upwards, right? So we assumed down here, we assumed in here, right, based on this guy right here, that it was going to be traveling down the length, right? We picked the position of the thing. It was positive X direction, negative Y direction, but we ended up finding that it's actually getting shorter when it's doing this right here. That's a not necessarily an expected result, I would think. But I guess it makes sense, right? Because these things are going to get, eventually they're going to get in line with each other, right? And so that would mean that this part of the thing would get shorter. Okay, I buy that solution. But then the next thing that we can do is we equate the J's. And when we equate the J, we have 2.598. So this was the I right here. And this is the J. I guess I'll put it inside a bracket, 0.5. And now we are able to stick in the negative 1.732 into there. And didn't really need that. And then it's going to equal the negative 0.5 omega CD. And we're able to find omega CD from that is negative 6.928 radians per second. And then, we're able to solve their problem. We could say, if we wanted to have the solution to this, we would plug in, once again, right, this guy right here, right? We'd plug that VCA in there, and we were able to get what VC with respect to A is a vector multiplying that negative 1.732 times the thing, ends up being negative 1.500 I plus 0.8660 J, and that's a meters per second. So if that was going to be part of the problem, was that part of the problem? No, they just wanted to find the angular velocities. So that was actually this guy right here was what we were trying to find for. To be continued. So I actually come to the next page. And now I want to do the acceleration analysis. Let's go purple. Oh, where did it disappear to? Where'd you go? Where's the mouse? Where'd the mouse go? There you go. There you go. Right. Let's go purple. Purple. And so we'll go the acceleration analysis. And we'll start with rod AC. And we write that the acceleration of C is equal to the acceleration of A plus the angular AC crossed with RC with respect to A minus omega AC squared times RC with respect to A plus the relative plus 2 times omega AC crossed with I'm getting very, very tired of making videos. And I think you're probably tired of listening to them. VC with respect to A relative, and that is a vector. Okay, so we could have gotten rid of some stuff in here. That was 0. Anything else? Oh, man. I guess that's why I picked this problem, was that there's lots of stuff that isn't 0. All right, so that was 0. So now we go 2, that's the angular acceleration, times our 0.6495 k crossed with I. And by the way, I guess I wait to the end right there, the semi-end, an ending thing, before I start giving my in-between numbers. 0.375, and that's k crossed with j, right? And then I go minus 4 squared, 0.6495 I, minus, right there, because that's the minus comes from that one right there, 4 squared negative 0.375, and that's j, plus dot dot dot. Okay, so continuing on here, so that was this term right here. Now we go to the relative acceleration, is going to be plus 0.866 times AC with respect to I, the magnitude I of that, plus negative 0.5 times AC with respect to I, J, plus dot 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 dot, plus 2 times omega, which is 4 times my negative 1.500 k crossed with I, plus 2 times 4, 0.866 k crossed with j. And now we could collect some terms. Why does that thing keep disappearing? I don't know. Well, it keeps disappearing on me. Why is it acting that way? I don't know. This guy right here is going to be 1.299. This guy right here is going to be j. He is going to be a minus 0.75, duh. But this guy is a minus I, so they cancel each other out. There's negative, negative. This guy right here, I get 10.39. We've got to remember he's negative. And this right in here, so maybe like make that negative right there. Okay, and then this guy right here, we notice that that minus is going to cancel out that minus, and so this is 6.00. And we don't need to do anything on this guy. Him right here, he's going to be a negative 12, and this is going to turn into a j, and this is going to be 6.928, and then this is going to be a negative I. So if we collect all of this stuff down in here, we come up with the acceleration of C is going to be, okay, I did an in-between step because I was really careful. Negative 16.57. This is like the hard part of being an engineer often, is the having to be methodical about things. It's irritating. It's annoying. But that's why they pay us the big bucks, baby. Yeah. You got to get good at just turning off that part of you that just can't stand doing tedious things. And when you get to that level where you could just hunker down and get to it, you become a better engineer and a valuable part of a team. All right, so what we need to do here is now, we want to remember this because we want to go to now bar CD. Boom, boom. And bar CD, it's got all the same equation there. It seems kind of silly to have to write this out. You start to lose patience with your instructor because he is being so tedious. Hey, my name's Ted, right? So that's like tedious, like Ted is tedious. Ted is tedious. I dare you to, if you actually are watching this, to actually come to me and stop me at some point and say, I heard you say that. You said Ted is tedious. You called yourself Ted. You're talking about yourself. You're talking to yourself in a room by yourself. You get that, right? Yeah, I know. All right, so this guy's 0. He's not 0. This is 0, and this is 0. So the acceleration, I'm trying to mix up the colors. Oh, I haven't used orange in a while. Acceleration of C based on the bar CD is going to be, well, we get 0 there plus this times negative 0.5. That's the K crossed with the I, and then minus 6928. That's something we found earlier. Squared times the position vector 0.5 is negative J. Oh, well, not J. It is I. Anything else? No, because that's 0 and that is 0 because this is 0. That's the reason why that's 0. Oh, that was gross. All right, so collect some terms here. This guy is going to turn into a J. Is that true? Yes. And this whole thing right there, we have that guy and that guy cancel each other out. So we have 24 right here, and that's I. So AC is actually going to be equal to 24I plus we'll put it there, minus 0.5, that's a good place for it, CDJ. So we equate this guy right here with this guy, the I's and the J's. So for in the I direction, I guess we'll go here. In the I direction, we have a negative 16.57 plus 0.8660 AC with respect to A is going to be equal to 24. We get AC with respect to A is 46.85 meters per second squared. So it's actually, looking back and seeing the thing, that means it's actually, even though it's moving in this direction, we decided that the relative velocity was moving in this direction, it's getting less and less because we got an acceleration in that direction. That's what that physically means. And now we can go in the J direction, J right here, and we're equating this spot right here with this guy, and you can tell the purpose of this is now we can get the angular acceleration. So we get negative 4.701 minus 0.5, and then 46.85 is what we just found, and it's positive, and it equals negative 0.5 times alpha CD. We get an alpha CD equal to 56.25 radians per second squared. And if you can believe it, that's the same as the solution manual. So that's one of the answers, and this is one of the answers. Well, actually, we should say that this is counterclockwise, and or we could give it, let's rewrite the thing. We did all that work. Why not get some credit for it? 6.93 K radians per second, and alpha CD as a vector is 56.3 K radians per second squared, and that's a complete answer. So let's take a look now at what the solution manual had to say. Let's take a look at how long this is. Woohoo, 25-minute example. Yeah, baby. So let's take a look at the book here. All right, so Hibbler, those are different bands I've been in. Books, not there. Okay, so we have dynamics and Hibbeler dynamics, and how many versions of Hibblers do I have? I think this is the 14th edition. And what did I say? This is problem 16. So they use chapter 16 is that. And so we open it up and we're waiting for you. It's what they used to do at the academy when you were a plebe, when you were a freshman. They used to have, we're waiting for you, when there was somebody who was like the last one out to, like, say, a formation. And so everyone would be chanting this together at the same time. We're waiting for you, we're waiting for you. Isn't that a great story? It was, if you happen to be that person, you start like to get that panicky feeling and start running. And now, you like when you really try to hurry, you kind of start tripping all over yourself, because you're like, extra trying hard. And it's that peer pressure thing that I don't think is very healthy. But that was going to a military academy. What a wonderful way to go to college. So here's the method that they use in Hibbler to solve this problem. You can see they have a different notation. They have things in a different order, but it's all the same thing. By the way, they're using the three-dimensional version of these equations right here. So you'll notice that we have that omega crossed to the parentheses omega cross right here. That is and that's capital omega. This will equate to being minus omega squared times that RC with respect to A. And then this is also what they're showing right here is this is the relative velocity, and this is the relative acceleration for these. But you can see how they set the thing up, and they walk through, and they get their position vector, and they write the thing through, and they keep them. Yeah, I guess they did. So they decided. By the way, they made their X in this direction. They made their Y in this direction. So that's why you're going to have different values for the position vectors, because they change the orientation of everything. And so they were able to get that omega. So they got the 6.93 radians per second. You'll notice, but that's the same idea right here. They equated the I's and the J's here up above. They did they did this part first. They did it for one bar, and they were able to do that right there. So that was okay. And then down to here, and they got the 56.2, and they got that same. So everything worked out well. Isn't that great? Okay. And there's no way to switch the camera on, so you can't see the beauty of this Les Paul. This is a beautiful, it's black. It's my favorite color of guitars. And let's see, this thing that I'm playing through is called a pod, and it's made by Line 6. So this is a vintage one now. I guess it's vintage now. This is old technology, but it's a nice thing just to use. I have like a little desk set up over here on this side of the guitar room. And so let's see, we'll put this into British blues setting right there, and I have it on a compressor. I'll put a little delay. Here's a delay. Here's a lot of delay. There's a tap tempo too. Here you go. So I'll tap very fast. Tap, 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 tap. So that's called a slap back. So you can hear that. I forgot to turn my microphone on. I wonder if I could just turn the microphone on like this right here. Will this be a better recording? This is a good test right here. Let's see. Here's the external microphone now. Let's see there. I often associate the Les Paul and this British thing with one of my very favorite live tunes of all time is Crossroads by Cream. That's with Eric Clapton. That was actually a modification. It wasn't really a cover because it's very different from the original. Robert Johnson from like 1929, one of the essential godfathers of the blues right here. But Clapton electrified it. Goes. I didn't do a very good job of this. I'm trying to play it right here. I'm trying to remember the song. That was terrible. Wow. I need to go back and practice that song again. So I wish I could go back and take it back. But no one's going to listen to this. So that's totally okay. I'm going to leave it alone. So thank you again. And boy, very impressive that you got to this part of the recording.